Hi there, we're Team 33. We're going to be giving our second presentation on the Space Shuttle Challenger disaster. Before we begin, we want to start with some introductions. I'll go first. My name is Usman Yaqut. I am a master's student in the software engineering department. Now I'll pass it off to my team members.
Hi, my name is Mahavir Kumar, and I am the student of University of Calgary with the Department of Civil Engineering and with my specialization in project management. And now I will pass to Ajay.
Hi everyone. I have completed my bachelor and currently pursuing my masters in civil engineering at University of Calgary.
Hi, myself Jiva. I'm doing my master's in chemical and petroleum engineering. And let's get into presentation.
Recording progress.
Here I would like to talk about Space Shuttle Challenger disaster. It was happened on January 28, 1986, resulted in the tragic death of all seven crew members when the shuttle disintegrated just 73 seconds after liftoff during mission STS-51L. The incident was a significant disaster in the field of space exploration and led to major changes in NASA's safety procedures and overall structure. The catastrophe occurred due to the malfunction of O-ring seal on the right solid rocket booster. The reason for this failure was the O-ring's loss of flexibility caused by the unusually cold temperature during the launch day, around 36 degrees Fahrenheit. Upon ignition of the rocket, the faulty O-ring led to a gas leak that ignited the external fuel tank, causing the shuttle to disintegrate. It is probable that the crew survived the first explosion but then lost consciousness as a result of cabin depressurization prior to shuttle cabin hitting the ocean. The crew's official cause of death was determined to be blunt force trauma from hitting the ocean and inability to survive in those circumstances. The catastrophe resulted in a total overhaul of NASA's safety and management strategies, placing greater focus on hearing from engineers and promoting open dialogue. The Challenger tragedy is still a vital example in a study of engineering ethics, risk control, and the significance of putting safety before deadlines. It highlights the impact of organizational pressure and the necessity of addressing issues brought up by technical experts. Thank you.
With regards to the space shuttle disaster of 1986, I would say there were some subconscious and cognitive biases, but I'm going to speak on a few. One of which would be the belief perseverance. The sole focus on data which supported the decision to launch the space shuttle while ignoring concerns raised by the engineers at Martin Call about the O-ring's performance in cold weather, I would say is a cognitive bias. Another would be the escalation of commitment. There was obviously a reluctance to cancel the launch after decision was made. I would say this was as a result of the heavy investments and planning commitments that had gone into it, disregarding the evident risk of the performance of the O-rings in extremely cold weather. And I think another would be the overconfidence. Confidence in the space shuttle's safety protocols and design led in the negligence of fully assessing the potential implications of launching on the day, which had an unusually cold weather. So at this point, I would like to pass it on to Mawar.
Thank you, David. Now let's move to the part number three, which is identification of system issues. Uh, During our research for the Challenger disaster, we have identified four different issues, and which are the following. Uh, Let me explain the point number one, which is engineering and design flaws. Mainly, uh, mainly the O-ring, which was one of the main component of the shuttle, and there was around two O-rings in the shuttle to for the uh, for not to escape the hot gases from the shuttle, but there were serious concerns about their safety, and That was the main issue and which led to the disaster. The second point is limited safety margin. During the construction of this shuttle, uh, uh, there were only few safety features which were incorporated by the NASA uh, planning team, uh, which were not sufficient uh, for in case of emergency, and this was a main issue by the engineering and designing team. The second point is communication breakdown. uh, Serious concerns were issued by the engineers, supervisors, and the contractors, which were the private contractors, which are building some of the key components of the shuttle, and uh, their concerns were not addressed by the NASA administration. Now, let's talk about the divergent communication channels. Uh, it was not decided by the NASA team before the flight, because they just made the decision one day before the flight operation, and that they are moving forward then for the launch. And there was many complex issues, and the communication channel was not up to the mark, and it was hindered by many problems. The third point is organizational pressure and culture. uh, as this program and this shuttle was delayed multiple times by the NASA administration, and they were not ready to delay for this time, and they were strict that they have the public pressure and political um, expectations from their government, that they need to launch the program, and they made compromises on the safety issues, and they go ahead with the project. Hierarchy in decision making. Actually, they were, as mentioned above, that safety features and concerns were issued by the engineers, which was not addressed by the administration, and it was the main thing, which was the issue and led to the disaster. Inadequate risk assessment. NASA progress was so bad that management, the process of risk management, was not involved in the shuttle program, and it was the main thing which can avoid the disaster, but they not move ahead with the program. Incomplete data on cold weather. On the day of the launch, it was too cold, and the temperature was around -40. That led to the disaster in the O-ring shuttle. Thank you.
Hi there. I'm going to be going through the lessons learned. Lessons learned are very important, especially for the Space Shuttle Challenger disaster. They give us the opportunity to reflect back at what happened and what we could do in the future to prevent a similar kind of tragic accident from happening. I have studied this case extensively and I've come up with 3 recommendations for lessons learned from the morbidity and morality presentation standpoint, which I think would be important. Let's go to the first one. The first very important lesson is that we need to prioritize safety over schedule. The Challenger disaster shows the importance of the need to prioritize safety, even if that means delaying the launch of the shuttle. The pressure from the management and higher ups was to adhere to the schedule. But from our engineering ethics, we see that the safety should be prioritized above all other factors, especially in high-risk industries like space exploration. The next lesson is that we need to empower engineering teams to make decisions so that we can prevent unsafe operations. Despite the engineers' recommendations against the launch, their recommendations were overridden. This, this, has highlighted, this has highlighted the need for a process to allow engineers to stop operations when they see that the safety has been compromised. We need to empower the technical teams so that they can halt operations if there's any kind of safety-related issue. The last lesson is that we need to establish clear communication channels for safety-related issues. The communication breakdown are significantly contributed to this disaster, and the warnings were inadequately escalated. We need to have transparent channels for communicating such type of issues. We need to establish structured communication protocols that are necessary to ensure safety warnings are properly conveyed and documented. This is the lesson learned. Now I'll pass it off to my colleague. Thank you very much.
Moving forward from the Challenger disaster, there are several essential measures that NASA and engineering teams can adopt to prevent similar tragedies. Let's discuss 5 key areas. First, safety protocols must be strengthened. This includes setting stricter launch criteria, especially in challenging weather conditions. By adopting more precise temperature thresholds and refining safety criteria, we can mitigate the risk of material failure in extreme conditions. Second, We need a culture that values transparency and open communication across teams. One major issue during Challenger mission was the engineers' concern about the O-rings were not sufficiently addressed. Establishing a safe environment where engineers feel empowered to voice safety concerns without a fear of consequences is critical to making safer decisions. Next, quality assurance processes must become more robust. Critical components like the O-rings in Challenger should be rigorously tested in various operating conditions. This increased testing would help to reveal any weaknesses in materials and system before they become threats to safety. Ethics must play a significant role in decision making. This involves regular training that emphasizes the ethical responsibility of prioritizing crew safety over mission success. By fostering a mindset of ethical decision making, team can better weigh the potential consequences of their choices, even under the high pressure circumstances. Finally, independent third-party reviews should be standard practice for critical mission elements. These reviews can serve a safety net, ensuring the decision making remains objective and transparent. By implementing these preventive measures, enhanced safety protocols, improved communications, strengthened quality assurance, ethical training, and independent reviews, we can take a vital step toward preventing another tragedy like the Challenger disaster. Thank you.